Hi everyone, welcome back to MATA35. This is lecture 4C. We're going to be continuing on and learning more about eigenvectors, eigenvalues, and a thing called an eigenbasis, as well as looking at some applications. Now, a lot of what we're going to be doing today was stuff we covered really fast in lecture 4B, but we're going to go through it a little bit more slowly since there seemed to be some confusion during the last class. So let's go ahead and get started, and I'm going to first start by talking about this. So this here is a map of UTSC. I know many of you haven't actually been to, or haven't officially physically come to UTSC, but this is a map of the Scarborough campus. And let me write on it a bit. So this here, the IC building, is where my office is at. So this is my office is in IC 343. And if we were on campus right now, that's where I would be having office hours. So you might notice that this is in map grid C2. So that's a coordinate that tells you where things are. And if you want the grid to look a little bit more like what you normally expect, you could draw the origin down here and have this be your XY axis. And this is 3, 4 on the grid. So you're 3 over to the right and 4 up, going upwards. So maps often start their grid going from the upper left instead of the bottom left, but it's the same sort of idea. But now, oh, actually, I still also have a picture. So this is the IC building. Hopefully you all will get to see it, as well as the other buildings on campus. So I know the biology department is actually more closer to the main campus, further down south, or not exactly south, but a little bit further down across Ellesmere Road from the IC building. But yeah, so the IC building is the one across the street. It's sort of near where the bus stop is. So if you take the bus, the 905 bus to the UT Scarborough campus, then you probably see the IC building. So this is where my office is, and if I want to tell you where I am, well, I could say I'm on map grid C4, C2, or it's 3 grid spots to the right and 4 grid spots up. Now, you'll notice that when we're looking at this map, there's also this legend up here that says that north is actually pointing this way. So north is not actually pointing up like it is on most maps. But now, you can also, of course, draw a map where the north is actually up, which is a little bit more standard. So here I've taken this from OpenStreetMaps, and you could draw yourself a compass rose, so that would look something like this. So this way is north, so this is actually a map that's pointing upwards. And again, we have the IC building, which is right here. So this is where my office is. And note that we've basically taken the entire map and we've turned it a little bit sideways so that north is pointing up. But of course, we can still figure out where we are by drawing out an axis. Drawing out some axes, and let's say, let's see, this is 1, let's say this is 2, 1, 2, 3, etc. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And so then, in this particular rendering of it, we're actually at position 2, 4. Yes, yeah. So you can think of these are just the various grid coordinates, and this is how you can specify a location or a point on this two-dimensional map. And now, of course, this is all really unsurprising, but the point is that we can specify a particular location given any particular grid system, right? It doesn't have to be north pointing north. It could also be this one, this weird one, where we have north is to the upper right. But either way, you can still specify a grid, and so long as you have 2 grid points, so long as you have 2 coordinates, you can specify a location. So these are what we need whenever we're specifying map coordinates. So on a 2-dimensional map, to specify a location, we need an origin point, and we need 2 independent basic directions, so for example, east and north, and then we need 2 coordinates specifying where we are. So now, when we draw this out, let's go back to something a little bit more standard. So if we draw this out like we do on the XY plane, and let's say we have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And so then you might have a point that lives, let me draw the point 2, 3, since I put 4 a little bit too far up. So this here is the point 2, 3. And we can specify it because we have this is our first basic coordinate, and this is our second one. So two independent basic directions. One is going to the right, and the other is going up. One corresponding to the x-axis, the other corresponding to the y-axis. And so this is equal to 2 times the first basic direction plus 3 times the second basic direction. And you can see this because if you go along, so you might go along 2 steps, 1, 2, to the right, and then you go up 3 steps, 1, 2, 3. Okay, so and we need 2 coordinates as well as an origin point. So you obviously have to specify some 0 point. So that's the origin point here. But now you might notice that I said just any 2 basic directions, and let me rewrite that just so I'm not covering up the thing. So 2 independent basic directions. But what if you chose 2 other basic directions? Could you still specify where you are on the map? And the answer is yes. So we saw this with the 2 different maps of the University of Toronto Scarborough, because even when we change the axes, so that's changing the basic directions, we're still able to specify the same point, the IC building where my office is. So let's try to specify the same point. I'm not going to actually rotate the entire thing. I'm going to keep my x and y axes in place. And let's see, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And we have our same point up here. So this point is still 2, 3. But let's try a different set of basic coordinates. So let's suppose one of our basic directions is this. Let's say our basic direction is 1, 1. So let's say this v1 is equal to 1, 1. And let's say we keep our second point the same. Let's say v2 is still 0, 1. Okay, so we can solve these basic coordinates, and then what's going to happen? Well, if you're trying to walk along, you're going to walk 1 step along here, 2 steps along here, and then maybe 1 step up. And so this is equal to 2 times v1, because the v1 coordinate is now up and to the right, so it's 1, 1 coordinate, plus just 1 copy of v2. So because we changed the basic directions that we're using to set our to describe our coordinates, we have slightly different values in our coordinates. It's 2 and 1 instead of 2 and 3, but we still can specify our location. So long as you have 2 independent directions, you can specify a coordinate on a 2D plane. This is, of course, really quite important, because if you don't have enough basic directions, for example, if you only have 1 basic direction in 2D, or if the 2 basic directions chosen are not independent, then we can't specify the location of any point. And let's see this. So if we happen to only have 1 direction, let's say we only had the direction 1, 1, so let's say v1 is equal to 1, 1. If we only had that point, then to this point here, 2, 3, this is off of the axes that we're allowed to use. So even if because everything, you can only specify points that are along this green line here. So unfortunately, you can't specify any point in 2D. You can only specify a subset of them. And so this is not a basis, because you don't have enough information. You can't ever use enough information with just 1 basic direction to specify a point on the 2D plane. Now, you end up with the same problem even if you have 2 directions if they're not independent. So for example, if you have 1 point that's v1 is equal to 1, 1, and then you try doing, let me put this in a different color. Let's do this in orange. And let's say you had v2 is equal to 2, 2. Oh, sorry, minus 2, minus 2. Well, then unfortunately, if you have this point 2, 3, it's still off of the line that you can specify, because these 2 aren't independent, and so they define the same line. And so this is what we mean when we say that we don't have a basis, because you don't have enough directions to be able to specify where your an arbitrary point is. So this brings us back to what we talked about last time, so basis vectors. So what exactly is a basis? Very good question, Jordan. So we have several different ways of describing what a basis vector is. So the standard basis, which is the one we normally use, is E1 through En, where each EI is the vector with all zeros except the 1 in the ith entry. So this is the normal x-axis for the first coordinate, y-axis for the second coordinate, z-axis for the third coordinate, and so on. And one obvious thing, and this is pretty easy to check, and we did this last time, is that any vector can be written as a linear combination of EIs. So you can add together some multiple of each of these EIs to get a vector. Now, an arbitrary set of vectors, v1 through vn, is a basis of Rn if every vector in Rn can be written as a linear combination. W is equal to c1 v1 plus through cn vn. So to repeat this a little bit and to answer Sam's question about adding these things together, note that if you have any coordinate in R2, so let's say this is 5 and 3, this is in R2, well, this is also equal to 5 times the first standard basis element, which is 1, 0, plus 3 times 0, 1. Okay? So that particular adding linear combination is pretty easy because you just take each of the coordinates and, well, that's the number of copies of that basis vector that you need to add together. Now, in the arbitrary setting, any set of vectors is a basis if you have exactly n of them for an n-dimensional thing, and you can add them together to give you any. So in the W equation, the v1 and v2 are the same. Yes, so the v1 and v2 and v3, etc., all the way through vn, correspond to the e1s through ens. We just use e1 through en for the standard basis because that's special notation for e1 through en, but you can do this with any n vectors if every vector can be written as a linear combination. Now note that this doesn't work for all combinations. Like we saw last time, if your vectors are linearly dependent, then you still can't write every vector. And so it turns out that what you need is this linear independence property. So any linearly independent set of n vectors in Rn is a basis for Rn. And a set of vectors is linearly independent if none of the vectors can be written as if none of the vectors in your set. So in your set, if none of the vectors v1 through vn can be written as a linear combination of the other vectors. There is a relatively quick way of testing this, which is you check to see how many different ways you can write 0. And so, obviously, you have to be able to write the 0 as a linear combination, because the 0 vector as a linear combination, because otherwise it wouldn't be a basis. But if there are multiple ways of writing 0, then and you only have n vectors, it turns out then it has to be linearly dependent. Okay, does anyone have any questions about what we mean by a basis? So by a basis, we mean that if you're in an n-dimensional space, it's a set of n vectors that are linearly independent. And if you have that, then you can write any other vector in your space as a linear combination of those vectors. Okay, so now we have several different properties we've thrown at you, and we should give you some examples and to illustrate what we mean by this. So now, remember, the vectors v1 through vn being linearly independent, well, they are linearly independent if you can take c1 v1 plus ... all the way to cn vn, if that's equal to 0 only when c1 and all the way through cn are equal to 0. Oh, can you show how you'd write the 0 vector? Yeah, so here we're doing something a little bit tricky, which is, remember how we use the variable I to refer to any matrix, any n by n matrix with zeros everywhere except ones along the diagonal? We're doing the same thing here, where we're using the 0 vector. So 0 as a vector is equal to 0, 0, 0, 0, etc. Okay, so just be careful when I use 0. If I'm setting a vector equal to 0, what I mean is the 0 vector. Okay, but now let's give a couple examples of this. So this is our test for linear independence is just setting these things equal to 0. So if we have an example here, let's try out these two vectors, 1, 1, and 2, minus 2. So we want to know if these are linearly independent, because if these are linearly independent, then they'll also be a basis, since we're clearly in a two-dimensional space, since these vectors have length 2. So what do we need to know? So we need to ask, if we have c1, 1, 1, plus c2, 2, minus 2, if that's equal to the 0 vector, 0, 0, which we're going to be call equal to 0, sometimes you might see this in a notation where someone will put like a little arrow above to tell you that it's a vector, but other times they just say 0 and have you assume that it is a vector of the right size. So that's what we're trying to solve for, and we want c1 and c2 to both be equal to 0. If they both have to be equal to 0, then these two vectors are independent. If they don't have to be equal to 0, then they aren't independent. Okay, so well, you'll notice that we can convert this equation here into a matrix equation, Actually, let me write it out slightly differently, just to make it a little bit more obvious, this conversion. So, if we multiply these things through, what you end up getting is you end up getting a system of equations, C1 times 1 plus 2C2 is equal to 0, and C1 minus 2C2 is equal to 0. And there are a bunch of different ways you can solve this. And I'll solve it a couple different ways just so that it's completely clear. So one way to solve this is to turn this into a augmented matrix. So you have 1, 2, 1, minus 2, 0, 0, and then you try to do row reduction. So in the very first step, what we'll do is, well, let's say the very first step, we're going to take R2 is going to be R1 minus R2. And when we do that, you end up with, you're not doing anything to R1. R2 is going to be 0, 4, 0. And then we can take R2 is going to be R2 divided by 4. So that's going to be 1, 2, 0, 0, 1, 0. And lastly, you can then do the Gauss-Jordan step of Gauss-Jordan elimination. And you'll take R1 is going to be R1 minus 2R2, and you're left with this, and so C1 is equal to 0 and C2 is equal to 0. And precisely because these C's are equal to 0, when this linear combination is equal to 0, you know that they are independent. So this implies that 1, 1 and 2 minus 2 are independent. Note that I solved this by using this augmented matrix. You could have also just directly solved the system of equations. And sometimes that's easier and sometimes that's harder. It just depends on how good you are with solving equations. So let's see another example of this. So let me give you an example with 3 vectors here. So let's say I have 1, 2, 0, 1, 0, 0, and 0, 1, 0. And we want to ask, are these linearly independent? Well, what we do is we set C1 times 1, 2, 0 plus C2 times 1, 0, 0 plus C3 times 0, 1, 0. And we want this to be equal to 0, where 0 here is the 0 vector. Okay, so well, let's rewrite this. One way of rewriting this is we could do it in the matrix format. So that would be 1, 1, 0, 2, 0, 1. 0, 0, 0 times C1, C2, C3 is equal to 0, 0, 0. And you could solve that using the augmented matrix. But of course, you can also solve these things without using an augmented matrix by just looking at the system of equations, which here are going to be C1 plus C2 is equal to 0, and 2C1 plus C3 is equal to 0. This system of equations, you can, after solving it, what you'll find is C2 is equal to minus C1, and C3 is equal to minus 2C1. And so this implies that solution is anything of the form C1 minus 2C2. Oh, sorry, minus 2C1. And so this is a solution. This is a non-zero solution, and therefore not linearly independent. Okay, because we have a solution to it where C1, C2, and C3 are not all equal to 0. Okay, so this is what you have to do to test if something is linearly independent. And the other question is, do you have the right number of vectors? So if you have an n-dimensional space, then you have to have exactly n linearly independent vectors for it to be a basis. If you have 2n, or n plus 1, then it's no longer a basis because you have too many vectors. If you have less than that, then you won't ever be able to get every single one of the coordinates. Just like what we were showing with a 2D map, you can't specify it with just a single coordinate. Okay, so let's have you all try this out. So, which of the following are bases? Is this a basis? Okay, so we have a couple of replies. So it looks like people are answering B. Yes. I mean, no, that is correct. B is correct. This is not a basis. And why is it not a basis? No. And you can see this a couple different ways. Well, one of the easiest ones is, well, minus 2 is equal to minus 2 times 1, 1. And so these are clearly not linearly independent. You could have also solved this by taking the time and actually writing out the system of equations, but this one here is pretty easy to see because one of your vectors is just a multiple of the other one. So no, these are not a basis. Okay, let's try again. What about these two vectors? Oh, let me reset this before you guys start replying. Okay, what about these two? Yes, these two are a basis. And why is that? Yes, and there are a couple ways you can see it. For two vectors, it's easy because you can just show that they're not equal to, that if one's not a multiple of the other, then they're linearly independent. But let's take a slower look at this. And so what we have is we have the augmented matrix 1, minus 5, 3, minus 4, 0, 0. And we want to show that when we convert this, so you can do, say, a step which is, let's have R2 be R2 minus 3R1. So that'll give you something that's 1 minus 5, 0, 0. And down here, this will be 3 minus 3, that's 0. Minus 3 times, that's 15. Minus 4 is 11, and so on. So we have a question here. Is basis synonymous for linearly independent? Not quite, though they are very closely related. So every basis has to be linearly independent. If a set of vectors is linearly independent, it's not necessarily a basis. A set of linearly independent vectors is a basis for an n-dimensional space if the size of the set is n vectors. So basis means it's linearly independent and you have as many vectors as the dimension of your space. Okay, let's try another one. Oh, yeah, just to finish this one off, this implies that that both of your coordinates are equal to 0. Yeah. Okay, what about this set? Is this a basis? Let me reset. Sorry, I need to remember to reset my chat every time. So what did I just tell you about bases and about the dimensionality of your space? What dimension are these things in? Okay, so we're starting to get a couple of replies. Okay, nice. Exactly. So this is in 2D, but we have 3 vectors. So 3 vectors in a 2D space, that can never be a basis. So no, because 3 vectors in 2D. Also, one other thing to note, if you have any 3 vectors in 2D, then they will be linearly dependent. It turns out that if you have more vectors than you have the dimensionality of your space, then they have to be linearly dependent, which is a nice little thing you can double check, though, and it's not so hard to prove, but we're not going to spend the time to do that in this course. Okay, so let's try this one. What about this? Let me reset before you reply. Okay, so it looks like we are already getting a couple responses. We're getting a couple of B's. Okay, yeah, so exactly. So this here is no, because it's 2 vectors in 3-dimensional space. Can you explain why 3 vectors in 2D are not? So there are a couple ways to explain it. The easiest one is if you have any 3 vectors in 2D, they will be linearly dependent. Because suppose you had 2 vectors that were linearly independent already. So in a 2D space, if you have 2 vectors that are linearly independent, then you can write any other vector in 2D as a linear combination of those 2 vectors, right? So that means your third vector has to be something you can write as a linear combination of the first 2 vectors, and so any 3 vectors can't be linearly independent, because you can always write the third as a function of the first 2 if the first 2 are linearly independent. Okay, let's try, I think I have one, oh no, I have 2 more here. So let's try this one. Let me reset before you reply. Okay, so we have a mix of responses here. Okay, so we have a few yeses and a few nos. So is this a basis? So note, this is in 3D, and this is 3 vectors. So it makes it a little bit more complicated, and you have to actually check whether or not these are linearly independent. So this is 3 vectors in 3D, so now we just need to check to see if they're linearly independent. So let's go ahead and try checking that. And so what do we have? I'm going to do this in matrix form just because it's a little bit easier to do this in matrix form. 1, 0, 0, 2, 1, 0, 3, 0, 1, 0, 0, 0. And well, what's my first step going to be? Well, I'm going to do 2 steps at once. I'm going to say R2 is going to be R2 minus 2R1. R2 minus 2R1, and R3 is going to be R3 minus 3R1. And what does that end up giving you? This ends up giving you 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. And so therefore, this is actually linearly independent. So the answer is yes. This is actually a basis. And that was a little bit harder because you had to actually check to see you had 3 vectors in the 3D space, so they could be a basis, but you have to check to see if they're linearly independent. Okay, let's give you one last one. So this one here. So now, if you've been paying attention, you should, let me reset before you answer. Okay, so I've just reset the chat. And so this last one here is going to be a little bit trickier, but if you pay close attention, well, we've already done this example. Okay, so we're starting to get some replies. And we're getting mostly B's. Yeah, we're getting B's, and the answer is indeed... Oh, what just happened? No. See previous slides. Because this is linearly dependent. Yeah, so the other way you could see it is in this particular case, all of your basis things are on the xy plane, and you don't have anything going into the third plane. And so even though I gave you 3 vectors, these are in 3D, but you don't really have anything into that third dimension, and so you can't, if I gave you the vector 0, 0, 1, there's no way you can take a linear combination of these 3 vectors to get that third vector, to get that 0, 0, 1 vector. And so there are several different ways of seeing it, and the easiest one is if you stare at this, you'll be like, oh, well, you can't get anything in your third dimension, which you have, and these are in 3 space. Okay, so that's what a basis is. It's basically just saying that it's a set of vectors that's just enough information to allow you to specify any point in space. You can't have too many vectors. You can have more vectors in the dimensionality. If you have too few vectors, it also doesn't work. And even if you have the right number of vectors, then you need to check that they're not on top of each other. So if they're linearly dependent, well, then you can't have, then they're also not a basis. Okay. So let's move on to the next thing. And so this was all sort of in like basis land and like coordinates and how you specify points on the map. And there's a lot more complicated stuff you could get into. We're not going to deal with it here, but this is all needed because we are going to go back to talking about what matrices do. So remember, matrices transform vectors. That's the entire point of matrices, right? And it turns out that we mentioned this earlier, but I'm just going to reiterate it. The columns of a matrix tells you where the matrix maps the standard basis vectors. So, for example, let me show you what I mean by this. If you have the matrix A is equal to 2, 1, minus 1, 0. Oh, let me get the right thing here. Minus 1 and 0. Well, if you multiply this by the first basis vector, that's 2, 1, minus 1, 0 times 1, 0. What do you get? You end up getting 2 minus 1. And if you do the same thing, AE2, 2, 1, minus 1, 0, you end up getting the second column, which, oh, that 0, 1. That's a 1 there. You end up getting the second column, which is 1, 0. So let's graph this out. Where do these things go? So if we're on the 2D plane, x, y, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So let's start out with this blue vector, which is, I'm going to start out with this 0, 1, since we did maps to 1, 0. So 0, 1 is here, right? And let's do maps to 1, 0, which happens to be our second are that E1, but that's by coincidence in this case. So that goes there. And where does that one go? So that one goes to 2 minus 1. Let me choose a different color. So that's 2 minus 1. So that goes there. Let's see, that's 2 minus 1. But what happens when we repeatedly apply this? So let's say a times, sorry, so let's say a squared E1. No. Let's just apply it again. What do we get? We want a times 2 minus 1. So that's equal to 2, 1, minus 1, 0 times 2 minus 1. Oh, so the standard basis vectors are always 1, 0, 0, 1, or 1, 0, 0, 0, 0, 1, 0, 0, 0, etc. So that's just by definition. That's what the standard basis vectors are. And it turns out that when you think about what a matrix means, one way of thinking about the matrix is it tells you where each of the standard basis vectors goes, and then the matrix tells you where that basis vectors goes, and then you can add them together, and that's actually another way of interpreting matrix multiplication. So when you multiply this out, you actually get 3 minus 2. So let me put that in. Am I out of colors? I guess I'll put that in red. So that's 3 minus 2. So 1, 2, 3 minus 2. And this happens to be equal to a cubed E2. Okay, so one of the things about matrix multiplication is that it's hard to see what happens as you repeatedly multiply, right? So if I ask you right now, what is a to the 100 E2? Well, I don't know the answer to that, because each time you multiply, it does some transformation and things move around, right? So that's the whole reason why eigenvalues and eigenvectors are powerful. Is because if you, and I mentioned this last time, if you have n distinct eigenpairs of n by n matrix A, we can interpret the action of A by what it does to the eigenvectors, because the eigenvectors form what we call an eigenbasis. So let's give a pictorial example of what we mean by this. So let's suppose we had a matrix A is equal to, I'm going to use 2 minus 1 minus 1, 2 here. And it turns out that this has two eigenpairs. They're going to be 3 minus 1, 1, and 1, 1, 1. And so if you notice, these two vectors are linearly independent. And so therefore, this forms a basis for the space. And because these are the bases that we form by eigenvalue, by the eigenvectors, we'll often call this an eigenbasis, because it's a basis formed of eigenvectors of a matrix that we care about. And so let's draw this out. Let me see if I can, hopefully I'll be able to draw this without making this too messy. Let's see, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, no. 1. I messed that one up. 1, 2, 3, 4. 1, 2, 3. Okay, so now the question is, we have these points. Let's say that we started with a point 2, 4. 1, 2, 1, 2, 3, 4. So we start with a point 2, 4. And note that we have these eigenvectors, and we can also specify things in terms of these eigenvectors, since they are some other basis, right? So I'm going to make this the green and this one blue. So I can draw an alternate set of axes. So let's say I drew an alternate set of axes corresponding to these two eigenvectors. Okay, so I'm drawing a new set of axes, and one of the things that's nice is that along these axes, I can also specify points along these axes. I think I messed that one up. And I messed this entire thing up. Let's try that one again. And we have the same on the blue here. 1, 2, 3. Okay, I definitely didn't draw these along the right points. So let me draw them correctly this time. So there, 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 there. Okay, so I have this alternate axis, and when you look at this, you'll notice that this point here is equal to going along this alternate axis, going along the green axis 3 steps, and going along the blue axis 1 step. And that we can figure out by just rewriting our original vector 2, 4 as 1 times minus 1, 1 plus 3 times 1, 1. So because this other, we can write all our points in this other basis, because it is an eigenbasis, so we can rewrite the point we care about as a function of this. So now when we apply this a and multiply a times 2, 4, well, we can use the distributive property, and this is now 1 times a times minus 1, 1 plus 3 times a times 1, 1. And well, that of 8, this is 1 times 3 times minus 1, 1, because that's an eigenvector, plus 3 times a times 1, 1. Oh, sorry, just 1 times 1, 1, because that's another eigenvector. And this is going to be equal to, well, 0, 6, once you've done that. And so when you multiply by a, what ends up happening is you can interpret the behavior along each of these different axes. So along the green axis, nothing happens, right? Because the eigenvalue is 1. So when you multiply it by it, it stays the same. But along the blue axis, it's going to go up 3 steps. So 1, 2, 3. Wait, sorry, 1, 1, 2, 3. And that's going to come along. And if I had drawn these better, which I didn't do, then it would have made a little bit more sense. 1, 2. This point goes to 1, 2, 3, 4, 5, 6. And this is going to be okay, so unfortunately I didn't draw it super well, so it's a little bit hard to see. But basically what we're doing is, what we're saying is that we can rewrite our original point 2, 4 as a in this new basis. So we have a new set of we have a new set of new coordinate system. And in that new coordinate system, you're going 1 along the green axis and 3 along the 3 along the green axis and 1 along the blue axis. So this here is, sorry, I put them in the wrong order, which makes this a little bit confusing. But, oh, what just happened? There. Right, so we have both the blue and the green axis, and along the blue axis, we're 3 steps down. And along the, along the green axis, we're 3 steps down, and along the blue axis, we're 1 step up. When we rewrite in this new coordinate system of eigenbases, then when we do the multiplication, it's really easy because we can scale independently along each of our axes. So when you do this multiplication, you just use the distributive property and spread things out. And therefore, you can quickly figure out what that point goes to. And it goes, that's why I messed it up. So that actually does belong to, no, that was right. Why do we have the multiplication by 1 and 3 twice? Oh, maybe I chose bad numbers. So let me highlight. So this 3 is this 3. And this 1 is this 1. Because the whole point of an eigenvector is that when you multiply a by that vector, you get lambda times that vector. And so a times this vector gives you 3 times that. And a times this vector gives you 1 times that vector. The 1 and 3 above, that's because the 1 and 3 here are because that's where the point is. So this is just solving for 2, 4, like what values do you need there? I probably shouldn't have chosen 2, 4 in retrospect because 2, 4 is... let me actually just change my points here. So let's say instead of using 2, 4, let's say I used... let me give another example, because if I do mess up this example, it'll get a bit confusing. Yeah, so 0, 6 is the vector for the original axis, because that's in terms of the original elementary basis. I have a couple more examples, so let's just go through them, and hopefully they'll become a little bit more clear after I give you a couple more examples. So we have our eigenbasis of a square matrix. If you have n linearly independent eigenvectors, those eigenvectors form an eigenbasis, which means that you can write any other vector in terms of multiples of those vectors, of the eigenvectors. There were a couple of things I mentioned last time. If two eigenvectors correspond to different eigenvalues, then they're independent. So if an n by n matrix has n different eigenvalues, then it has to have an eigenbasis. You can also solve for an eigenvector by setting ax equal to lambda x. So if lambda is an eigenvalue, then you will have at least one free variable after solving, because any constant multiple of an eigenvector is an eigenvector. And if you have k free variables, you can find k linearly independent eigenvectors by setting, for that one eigenvalue, by setting each free variable to 1 and all others to 0 repeatedly. Okay, let's try this out. So I had this example last time, and it was the reason we did this lecture, because people were really confused. But let's try this out again. So does this have an eigenbasis? So if you find the eigenvectors of this, are they linearly independent? So remember what we just said. If you have different eigenvalues, then you have to have linearly independent eigenvectors. And this is a diagonal matrix, and therefore the eigenvalues are just 1 and minus 1. Just a moment. Okay, yes. So it looks like people are getting the right response. So the answer is yes. And the reason for this is because we have two different eigenvalues. Just a moment. What happened? Something went wrong here. Okay, something went wrong with my notes, but I'll deal with it. Okay, so we have our yes, because we have two different eigenvalues. And let's try this again. So what about this one here? So this one's going to be a little bit harder, because, of course, we have two of the same eigenvalue. So if you want to solve for this, you need to do a little bit more work. Okay, so a lot of people are answering B. Oh, sorry, it's not updating. Let's go ahead and force update this. Yeah, so everyone's answering B, and that is correct. And the reason for this is that if you were to solve this, you get 2, 0, 1, 2 times xy is equal to 2x, 2y. And we have 2x is equal to 2x, and x plus 2y is equal to 2y, which forces x to be equal to 0, and therefore our vectors are 0, y, and so 0, 1 is our only eigenvector. So the answer is indeed no. Okay, this one's a little bit trickier, because the eigenvectors are a little bit harder to see immediately. So for this one, you need to actually compute the eigenvectors as well. Okay, so for this one, as I was saying, you just need to compute the eigenvectors. So let's do that. So 1 minus lambda to 4 minus lambda. This is going to be equal to 1 minus lambda times 4 minus lambda minus 4 is equal to 0. So this is 4 minus 5 lambda plus lambda squared minus 4 is equal to 0. Lambda squared minus 5 lambda is equal to 0. Lambda times lambda minus 5 is equal to 0. So lambda is equal to 0 and 5, 2 eigenvalues. So yes. Okay, and I think I have one more here. So, does this one have two independent eigenvectors? Or, sorry, not two independent. Does this one have an eigenbasis? So in this particular case, you would need three different eigenvectors. Okay, so we're already getting a couple responses. It looks like people are saying A. And yes, the answer is yes. Even though you only have two eigenvalues, the answer is yes. And you can see this because 1, 0, 0, 0, 1, 0, and 0, 0, 1 are all eigenvectors. And you could have solved for these. You would have solved for the eigenvalue 2 and gotten two linearly independent eigenvectors out of it. Okay, so let's keep on going. So last time I talked about these population growth rates, and the reason for this, the reason why eigenvalues and eigenvectors are super important, is because it allows you to quickly solve for a population vector at time t. So let's work through that example again, but this time in multiple different steps. So assume that we have an age-structured population model for birds where we've divided up in this way. We have a different starting population vector of 6, 0. What is the population after 10 years? So there are multiple steps. The first step is you need to convert this into a math problem. So we have our population vector of young and old. This is 6, 0, our population vector. And we have our Leslie matrix. And note that this here is going to be 1.5 because 1, 0.5, 1. Since this top here is the number of hatchlings from young, this is hatchlings from old, and this here is survival of hatchlings to adults. And this here is survival of adults. Okay, and what we want to do is we need to find L10 to the 10th power of P0, which is going to be equal to P10. The first thing we're going to do, which we did last time, so I'm going to do it pretty quickly, is we have to do an eigendecomposition of this matrix. So for this matrix, you get eigenvalues, and we can solve this, and what you end up getting is you get eigenvalues lambda 1 is equal to 2, and lambda 2 is equal to 0.5. We did this in last week's notes, so I'm not going to repeat them. And you get eigenvectors, which are going to be for lambda 1, you end up getting v1 is equal to 2, 1, and for lambda 2, you get v2 is going to be equal to minus 1, 1. Okay, so this is just repeating the stuff we did last time. Now, the step that I sort of did super quickly last time, which we'll do a little bit more slowly, is you need to rewrite your original vector as a linear combination of your two eigenvectors. So in order to do this, what we're going to take is we're going to take c1 times 2, 1 plus c2 times minus 1, 1 is equal to 6, 0. Now this, of course, just implies that we have the matrix 2, 1, minus 1, 1 times c1, c2 is equal to 6, 0. Or we can also write it out as 2c1 minus c2 is equal to 6, and c1 plus c2 is equal to 0. I'm going to solve this by adding these together. So you'll end up getting that 3c1 is equal to 6. So c1 is equal to 2, and c2 is then equal to minus 2. And therefore, we know that 6, 0 is equal to 2 times 2, 1 plus, minus 2 times minus 1, 1. So someone asked the question of how we know those numbers. You know these numbers because you have to solve the system of equations to figure out what the coordinates are in front of the eigenvectors. And now to solve it, all you have to do now is P10 is equal to L to the 10 times 6, 0, which is equal to L to the 10 times 2 times 2, 1, minus 2 times minus 1, 1, which is going to be equal to, well, L to the 10 is, these are the eigenvectors, and so this is equal to 2 times 2 to the 10 times 2, 1, minus 2 times 0.5 to the 10 times minus 1, 1. And this is going to be equal to 2 to the 11th times 2, 1, minus 2 to the 1 over 2 to the 9th times minus 1, 1. And this is about equal to 4096 over 2048 minus 1 over 2 to the 9th of minus 1, 1, which is about equal to 4096 over 2048. Okay, so I was going to ask you to try this out, but we're running a little bit low on time. So instead, I will just walk you through the second line. Yeah, so let me walk you through this one a little bit more carefully instead. So when you're looking at this, let me erase this and rewrite it. So when you're looking at this vector here, this is equal to 2 times L to the 10, 2, 1, minus 2 times L to the 10, minus 1, 1, right? But note that these two things are eigenvectors, right? So you know that because these are eigenvectors, what you know is L times 2, 1 is equal to, what was the, 2 times 2, 1. And L times minus 1, 1 is equal to 1/2 of minus 1, 1. Right? So each time you multiply by it, you get 2 times 2, 1, or you get 1/2 times minus 1, 1. But you're doing this 10 times. And so because you're doing this 10 times, what you end up getting is this is equal to 2 times 2 to the 10th, 2, 1, minus 2 times 1/2, 1 over 2 to the 10, times minus 1, 1. Did that make a little bit more sense? How did you get the 1/2 again? So the 1/2 is because when we computed the eigenvalues, the eigenvalue of lambda 2 is equal to 1/2. So this is where the eigenvalues are. So when we computed the eigenvalues for this eigendecomposition, you had 2 and 1/2. And of course, to solve that, what you do is you take 1.5 minus lambda, 0.5, 1 minus lambda. You take that determinant and you set that equal to 0 to get the two eigenvalues. So now, when we're doing this for any particular example, what you'll find is that you just need to rewrite your original population vector. So for this other example, the population vector, I flipped it, and so we have 6 adults and 0 young. When we rewrite that, you'll find that this is equal to 2 times 2, 1 plus 4 times minus 1, 1. So you can check that this actually works out. And what you end up getting is P10 is equal to, well, 2 times 2 to the 10, 2, 1 again, plus 4 times 0.5, so 1/2, because that's that eigenvalue, to the 10 minus 1, 1. And that's also about equal to 40962048. And one of the really important things about these eigenvalues and eigenvectors is you'll notice that it doesn't really matter that we change the number, the coordinate corresponding to the 0.5 eigenvector, because exponentials grow super fast, and so the long-term growth rate is dominated by the largest eigenvalue. Let me do one more slide before we, 1 or 2 more slides before we head to office hours, and then I can go back and explain in a little bit more detail. So if we had a 3 by 3 Leslie matrix, which I haven't given you, but you should be familiar with them. So we have 3 different life stages: newborns, juveniles, and adults. At long time scales, to find the ratio, we don't know what it starts out with, but we're just going to assume that at long time scales, you can assume that the ratio corresponds to the top eigenvector. Because the growth rate is dominated by the biggest eigenvector, since that is the biggest thing before the exponent. So in order to solve this, you solve minus lambda, 6, 8, 0.5, minus lambda, 0, 0, 0.5, minus lambda. This is going to be equal to minus lambda cubed plus 2 plus 3 lambda is equal to 0. And you can solve this by using the 3 by 3 determinant rule. So lambda cubed minus 3 lambda minus 2 is equal to 0. Factoring this is a little bit complicated. I'm going to introduce a term, lambda squared cubed plus 2 plus lambda squared minus lambda squared plus 3 lambda plus 2 is equal to 0. So we're just factoring this out now. And you're left with lambda plus 1, lambda squared minus lambda minus 2. So you get lambda plus 1 and lambda plus 1. Lambda minus 2 is equal to 0. So lambda is equal to minus 1 and 2. So now this 2 is the important part, because that's the biggest eigenvector. So if you want the long timescale behavior, you just need the biggest eigenvector in absolute value. And so then you solve for this. So solve for eigenvector corresponding to eigenvalue of 2. And when you do that, you find this eigenvector is equal to 16, 4, 1. You find this eigenvector, and when you solve that eigenvector, you know the long time scale population ratios and population growth. And so at long time scales, the ratio of newborns to adults is 16 to 1. Because when you use these eigenvectors, you can get the long time scale behavior. Okay, and I will... because 2 is bigger. So you find the eigenvector corresponding to the biggest thing, because if you take a big number and take an exponent, it's going to grow faster than a small number to an exponent. And let me do one more slide, and then I'll go to office hours, and I'll go back and explain everything that is confusing. So this advanced topic, this will not be on the quiz. I just want to mention this because there were some questions about this earlier. So we've talked a lot about scaling by a constant multiple. What happens if the numbers aren't real? So if you have 0, minus 1, 1, 0, this turns out to be a rotation operation. So if you have something here, that's going to rotate over by 90 degrees to a new vector there. And if you have a square, a rectangle, that's going to rotate into this rectangle. And if you notice what the eigenvalues are, minus lambda minus 1, 1 minus lambda, this is going to be lambda squared plus 1, which implies that lambda is equal to plus or minus I, the imaginary root. And what it turns out is that imaginary eigenvalues correspond to rotations. And complex eigenvalues can be a combination of scaling and rotation. This will play a role later when we start talking about autonomous systems. I will not have complex eigenvalues on the quiz. And with that, I will go ahead and go back and answer a few questions you guys had about eigenvectors and eigenvalues. So let's go back and to this one here, where I sort of skimmed through this quickly. And I will start talking. So first, class is dismissed, so you can leave now. I'm just going to go back and show you some of the steps over again for those of you who want to stick around. So sorry I went a little bit over, but this material seems this is difficult material. So okay, so let's go back to this particular example and let's walk through it a little bit more slowly. We want to do an eigendecomposition, which means we want to find the eigenvalues and eigenvectors, right? So, how do you find the eigenvalues? Eigenvalues. In order to find the eigenvalues, you just need to take the determinant of 1.5 minus lambda, this is 1, 0.5, and 1 minus lambda. Okay? And you need to set this equal to 0. So this is equal to 1.5 minus 2.5 lambda plus lambda squared minus 0.5 is equal to 0. When you factor this out, this is lambda squared minus 2.5 lambda plus 1 is equal to 0. So this is lambda minus 2 times lambda minus 0.5 is equal to 0. Or you can use the quadratic formula. And so then lambda 1 is equal to 2 and lambda 2 is equal to 0.5. In order to get the eigenvectors, well, we have two of them, right? So let's try lambda 1 is equal to 2 first. So lambda 1 is equal to 2. And so that gives you a matrix, which is going to be 1.5, 1, 0.5, 1 times xy is equal to 2x and 2y. When you solve this, what you end up getting is you get 1.5x plus y is equal to 2x, and therefore you get that 0.5x is equal to y, and so you end up getting a vector x 0.5x, which gives you either 1, 0.5, or I wrote it as 2, 1. So you can pick and choose, and you can scale it a bit to get rid of the decimals. And for lambda 2, that was equal to 0.5, and we had 1.5, 1, 0.5, 1, x, y is equal to 0.5x and 0.5y. And when you solve this, you'll end up getting that x plus y is equal to 0, or x is equal to minus y, so v2 is equal to minus y, y is equal to minus 1, 1. Okay, and so that's how we get the eigenvectors. And then once we have the eigenvectors and eigenvalues, those things go straight into here when we multiply by the matrix, say 10 times or 100 times. All you have to do is take powers instead of actually having to do a matrix multiplication, which is why these eigendecompositions are powerful. And I think I should end my recording there. Thank you very much.